In this video, we'll go through question 11 from the 2017 Mathematics Extension 1 HSC exam. So, question 11, part A. The point P divides the interval from A, -4, -4, to B, 1, 6, internally in the ratio 2 to 3. Find the x-coordinate of P. Okay, so here we're dividing an interval in a given ratio, and we have a formula for that. And if you don't remember the formula, it's actually okay in this case because it is given in the formula sheet. But I would recommend that anyone doing this course should know this formula. All right, so the formula says that if I want to divide an interval, so let's say it's going from x1, y1 to x2, y2, and we're dividing it in the given ratio m to n. Okay, if we wanted to do that, then the coordinates of the point which divides it is going to be given by this formula: mx2 plus nx1 over m plus n, comma my2 plus ny1 over m plus n. Okay, now in our case, what do we have? We have a, which is -4, -4, and b, which is 1, 6, and we're dividing in the ratio 2 to 3. And the question also only asks for the x-coordinate. So the x-coordinate of the point P is going to be given obviously just by this part here. Okay, so we can just go ahead and apply that. Actually, I don't even need this. So that'll be m. Now, what's our m? Well, this is m for us, that's n for us. So it's going to be 2 times x2, which is 1, plus n, which is 3, times x1, which is -4, divided by m plus n, 2 plus 3. Okay, so I have 2 plus -12, which is -10 on 5, which is -2. Okay, and that's the first one. The next part, differentiate tan inverse of x cubed. Okay, so I want to differentiate this function, and now this function is actually a composite function. It consists of an inverse tan and x cubed. So when we differentiate composite functions, we need to use the chain rule or the function of the function rule, whichever you call it. So the first thing that we do is we differentiate tan as if it was just a normal tan inverse of x. So that's going to be 1 divided by 1 plus, now it's going to be the argument of the inverse tan, which is x cubed. The argument just means the stuff inside the brackets. And then that has to be squared. And then we multiply by the inside derivative, which is the derivative of x cubed, 3x squared. Okay, so we have 3x squared divided by 1 plus x to the 6. And that's the final answer for that one. Okay, part C, solve 2x over x plus 1 greater than 1. Okay, let's write that down. 2x over x plus 1 is greater than 1. All right, so we have an inequality here, and we have an unknown in the denominator. So we need to eliminate that unknown in the denominator. We need to get rid of it. Now, to get rid of the unknown here, if this was a normal equation, we would just multiply by x plus 1. However, in this case, because it's an inequality, we can't do that because we don't know if x plus 1 is going to be negative. If it was negative, that would be a problem because we'd have to change the sign. So to ensure that it's always going to be positive, we multiply by the denominator squared. So that means I'm going to multiply by x plus 1 all squared. So on the left-hand side, I'll be left with 2x times x plus 1 because one of the squares will cancel with the denominator, and on the right-hand side, I've got 1 times x plus 1 squared. Now I can go ahead and expand this out and simplify. So that'll be 2x squared plus 2x is greater than x squared plus 2x plus 1. I can cancel a 2x and a 2x here. I'll bring everything over to the left-hand side, and I get x squared minus 1 is greater than 0. Now, how do we solve something of this form? Well, we can sketch this. If I just have a look at y equals x squared minus 1, and I sketch it here, this is quite an easy function to sketch. It has to just be very rough. this is the point -1, this is the point 1. Now I'm looking for wherever this function is going to be greater than 0. Okay, and that clearly occurs in these parts here. So that's where my function is greater than 0. And of course, I'm being very careful to not include these points here. Okay, because here it's not greater than 0, it's equal to 0. So my x values that will give me this function being greater than 0 are going to be x greater than 1 and x less than -1. So therefore our solution is x is less than -1 and x is greater than 1. And we have strict inequalities. And that's the end of part C. Okay, part D. Let's have a look. Sketch the graph of the function y equals 2 cos inverse of x. Okay, y equals 2 cos inverse of x. Let's move this up a bit. All right, before we go ahead and sketch it, let's see what we already know about inverse cos. So let's just consider inverse cos of x by itself, without multiplying it by 2. That's what I should say. Okay, so the domain. What's the domain? Well, we know that the domain of a cos inverse function is going to be between -1 and 1. So the possible x values are between -1 and 1. And the range is going to be, our y value is going to go between 0 and pi. Okay, this is something that you should just be very familiar with, that it's almost immediate for you to work out. So what's the effect of multiplying this whole function by 2? Well, it's not affecting anything to do with the x values, it's only affecting the y values. So for us, we still have this domain between -1 and 1, but now our range has changed. The possible values of y are all being multiplied by 2. So the lowest value will be 0 times 2, which is still 0, but the highest value is going to be pi times 2, so 2 pi. And now we're ready to sketch it. So this is going to be a very rough sketch, but it should be good enough. So I have 1 here and -1 there. And let's extend that just a little bit. This point here will be 2 pi. This will be pi. And this will be obviously 0. And it's going to look something like that. Okay? So if this was the cos inverse, the only difference would be that this is pi and this is pi on 2. However, in our case, we've multiplied everything by 2. Okay, that's question D done. Let's move on. Question E, evaluate the integral from 0 to 3 of x over the square root of x plus 1 dx using the substitution x equals u squared minus 1. All right, let's write that down. The integral from 0 to 3 of x over the square root of x plus 1 dx. And we were given an integral, a substitution to use for this integral, which was, not u, it was x equals u squared minus 1. Okay, so we're given a substitution. First thing we have to do is differentiate that. So we get dx on du equals 2u. And so that gives us dx equals 2u du. Okay, that's good. What else can we see? Well, let's rearrange this for u, and we'll get u squared equals x plus 1, which means that u equals the square root of x plus 1. And the reason we do that is because now I want to change my limits of integration. So when x is equal to, let's write this here, when x is equal to 0, u is equal to the square root of 0 plus 1, which is just 1. And when x is equal to 3, u is equal to the square root of 3 plus 1, which is 2. Okay, now we can make our substitutions. What's x equal to? That's u squared minus 1. We know that the square root of x plus 1 is equal to u, and dx is equal to 2u du. I can cancel this u here with that u there, and I can bring the 2 out the front. And so I'm left with integrating u squared minus 1 du. Let's just move this up a little. Okay, this is not too difficult. The integral of u squared is u cubed on 3. The integral of 1 is u, between 1 and 2. We substitute the top number in first. That gives us 2 cubed, which is 8 on 3, minus 2, minus, substituting 1 in, gives us a third minus 1. Okay, so I have 8 on 3 minus 1 on 3, that's 7 on 3. Minus 2 minus minus 1 is plus, is minus 1. So yeah, I have a minus 1 here. So inside the brackets I have 4 on 3, and I times that by 2, I get 8 on 3. And that is the answer. Okay, the next one, part F. Find the integral of sine squared x cos x. Okay, and that's all that the question says. So just, what is this equal to? Okay, so there are two ways that we can do this, but they are technically kind of just the same thing, but one is a shorter way of doing the other one. So this here would actually involve a u substitution. Now, how do I know this? Well, firstly, it comes with a bit of experience. But I can see here that I have some function that's being raised to a power. Okay, I'm just calling the power n in general. And that function is f of x equals sine x. And I can see that that power of that function is being multiplied by cos of x, which just happens to be the derivative of sine of x. So if f of x is equal to sine x, then f dash x is equal to cos x. And this is very helpful because I can make a u substitution. I can say let u equal to sine of x, then du equals, du on dx is equal to cos of x, which means that du equals cos x dx. And how convenient that this cos x dx is exactly what I have right at the end here of this integral. So that means that this is going to be equal to, well, sine is just u, so sine squared is u squared, and then cos x dx is exactly du. Okay, and then the integral of u squared, well, that's just u cubed on 3 plus c. But now I have to substitute back into my original variable. So I'm substituting u equals sine x in, and I get sine cubed x on 3 plus c. And that's the final answer. Now, some people might be able to go straight from here down to here in one step, and that would be perfectly fine because this is only worth 1 mark. And so they're only looking for the final answer being correct. Okay, and that's question F. And now let's have a look at part G. The probability that a particular type of seedling produces red flowers is 1 over 5. 8 of these seedlings are planted. Part I, write an expression for the probability that exactly 3 of the 8 seedlings produce red flowers. Okay, so we've planted 8 seedlings. So I have 1, 2, 3, 4, 5, 6, 7, 8. 8 possible seedlings here. And I want 3 of these to be red. So I might have this one being red, I might have this one being red, and maybe this one is red. Okay, so what's the probability of getting a red flower? That's going to be 1 out of 5. So therefore, obviously, the probability of not getting a red is going to be 4 out of 5. So that means in this one here, which in the first one, which isn't red, I have a 4 out of 5 chance. This here has a 1 in 5 chance. This is a 4 in 5, a 1 in 5. And you can see what I'm doing here, 4 in 5, 4 in 5, and 1 in 5. Okay, and that is just for one case. Now, how many ways can I rearrange these R's out of these 8 possible positions? Well, I'm choosing 3 out of 8, so that's going to be 8C3. So, therefore, my probability of having exactly 3 red is given by the following. Like I just said, I have 8C3 ways of choosing 3 of these seedlings to be red out of 8. So that's 8 choose 3. And then there's going to be, well, I have 1 here, 1 here, and 1 here. So that's a fifth to the power 3. And then I have 4 out of 5 to the power 5. Right? And that's your final answer. You don't actually need to evaluate that. The next part says, write an expression for the probability that none of the 8 seedlings produces red flowers. So if none of the 8 seedlings produces red flowers, that means I want every single one of them to be not red. That means each one has a 4 out of 5 chance. So this one's very simple. It's just 4 out of 5 times 4 out of 5 times 4 out of 5 8 times. Or in other words, 4 out of 5 to the power 8. Okay, and that's all there is to that one. And the third one, write an expression for the probability that at least one of the 8 seedlings produces red flowers. Okay, so the probability of at least one being red is going to be equal to, now, here's a very important thing when you're doing probability. Whenever you look at a question and it asks you for the probability of at least something, that usually triggers the use of complementary events. So what's the complementary event of at least one being red? The complementary event is the fact that none of them are red. So this is going to be equal to 1 minus the probability of having no reds. Okay, which is what we just worked out in the question above. So this is 1 minus 4/5 to the power 8. And that is the end of question G and the end of question 11.